All right, so we had begun a discussion of the Boltzmann transport equation for understanding transport of electrons under reasonably large amounts of scattering events. It's kind of the if I look at transport regimes, there is a very pure no scattering ballistic regime where electrons are moving effectively like waves. They have wave-like properties. You can think of them as single modes going in a optical fiber or something like that. So there's analogies with light. They undergo interference, diffraction, that sort of thing. Right now, so what we are looking at is a diffusive regime where there is a reasonably large amount of scattering, but still, meaning the wave fronts may be scattered by angles and things like that, but the electrons still behave like waves. I mean, they're like a wave propagating in a disordered medium. An analogy may be if you have a glass of clear water and you're shining light through it, can go through right through it. But if you have dilute concentrations of particles floating around in the water, or milk, a little bit of milk, you see that the amount of light that goes through reduces because of scattering and redirection. So that's the diffusive regime. And the other extreme is when you have when electrons are still waves. I mean, electrons will always be waves in a crystal, except they get completely localized. They cannot move. So that's something we are going to talk about a little bit later. So where also related to defects or highly disordered materials, even though you have what may be considered initially as a conduction band, or because of strong electron-electron interactions, they end up forming closed loops or standing waves, and they're not able to propagate. So we are looking at Boltzmann transport equation is capable of handling these two very well. And in the localization, we'll see that there are a couple of other things one may need to consider. In the diffusive transport regime that we are discussing at this point in time, it's most of the properties are characterized by certain scattering times, right? And that's something we are looking at calculating. We derive the Fermi golden rule for calculating what this time is for microscopic for scattering between quantum states, k to k prime. And so we have a recipe now of calculating the rate itself, and we are trying to see how to include that in a bigger picture of transport parameters and things we actually measure in experiments. So that's what we are trying to do at this point. So how to relate this microscopic picture to maybe things like mobility or saturation velocity of electrons or electrical conductivity, and we'll see that pretty much all transport parameters, thermal conductivity, Seebeck coefficients, all that stuff can be calculated using this, understanding the microscopic scattering rates and combining that with this Boltzmann transport equation that keeps track of the population of the electrons in the K space, and then you sum over each of these parameters. In the end, is a sum over the K space of the occupation of the electrons in whichever way they're distributed, and that distribution function is what we get by the Boltzmann transport equation. So that's kind of the again a summary of what we are doing now. Today I want to give a few examples of application of this procedure to calculate mobilities. You are also doing that in the assignment currently, and with a few concrete examples related to impurity scattering, phonon scattering, and such. And I will discuss what I wanted to do is in the next week I wanted to get started on the next topic, which has got to do with one regime of the metallic transport, which is highly correlated. So I'll discuss most of this stuff today in the diffusive transport regime or in the ballistic transport regime, and then next week the plan is we'll talk about correlated transport in terms of superconductivity and such, and then I wanted to move into the topologically protected transport mechanisms and such. So what over the last decade people have realized is even in the presence of defects, there are some things you can do with the symmetries that are inside the crystal, be it translational symmetry, time reversal symmetry, etc., etc. You can play with them, and the band structure can be engineered in a way that you can avoid scattering like this. Even if there are defects, the electrons manage to avoid scattering, and that's an evolving idea, and people, it's an active area of research right now, and that's the topic we will look at some point a little bit later. Next week I'll talk about superconductivity, and the week after we get started on the topologically protected transport and such thing. Okay, so with the Boltzmann transport equation, I want to kind of show you what we are going to end up with, and then we go through and look at how we are, what's the reason behind, or rather the quantitative aspect of it. So if I look at a transport parameter, if you remember, we had started with talking about if I have a bunch of electrons, and even in a semi-classical sense, if I were to track the ensemble velocity of these electrons as a function of electric field that we have applied in volts per centimeter, we had already kind of set up the transport problem in most materials as it will look something like this in a crystal, electrons going in a crystal. And this slope was what we call as the mobility, this velocity towards which the electron, the net velocity, there's a saturation velocity, and we talked about in most semiconductor or semi-metals, the saturation velocity is of the order of 10 to the power 7 centimeters per second, of the order. Could be 10 to the power 3 times that, or maybe 9 times 10 to the power 6 or something like that. That's the order of magnitude. And the mobilities can range widely from low values of 1 centimeter per square per volt second to, at room temperature, it can go up to maybe about 100,000 or 50,000 or something like that centimeter square per volt second. So let's say of the order of 10 to the power 3 centimeter square per volt second is the order of magnitude. This is at room temperature, but if I start doing these measurements at different temperatures, for example, the mobilities in doped semiconductor crystals may look something like this, where mobility versus temperature, there is a decrease at high temperatures, and there's also a decrease at low temperatures. And the room temperature may be somewhere around here, for example. So we'll see that the mobility has, in the end, the effect, one can think of it as just the electron charge times scattering time, some sort of a average over the effective mass. So the scattering time is dependent both on the ensemble scattering time is dependent both on the density of impurities, or how defective is the crystal, or if very high temperature, how much phonons there are. But it's also dependent on the carrier density, electron density, mobile electron density, in the sense that if I have charged impurities, that are scattering the electrons, if I have more electrons, then they can screen the charge impurities. The mobile electrons can screen them, so that effect can actually play a big role. But if my carrier densities are extremely large and you start approaching metallic carrier densities, or if the electron density, so the temperature dependence in a lightly doped semiconductor is such that the electron density versus temperature, at low temperatures you get very low densities and then it increases and finally all the dopants are ionized. So the carrier density kind of changes like that in a lightly doped semiconductor. And then the mobility will look something like this. What happens is the ionized impurity scattering gets more and more severe because there are fewer and fewer free carriers to screen. And at the same time, the temperature is low, so their effective velocities are also low. And even in a classical sense, if I have a charged impurity and if I have a point charge like that, and I'm shooting electrons, in a classical sort of physics, if I have a very high velocity of the electron, it will scatter by a small angle. But if I have a very low velocity of the electron, it can actually scatter by very large angles. So that's a classical problem, and it carries over to the quantum problem too. So higher is the temperature, higher is the effective kinetic energy of the electron, and it can scatter less. So that's why the mobility goes up like that, as you're increasing the temperature with impurity scattering. Yeah.
I was going to say, can you just discuss the significance of that peak?
We are going to look at the details. So this part typically would be a phonon, some sort of a phonon, acoustic, optical, and this part is typically due to an impurity scattering. And you, depending upon the phonons, you in a chosen material you cannot really change much. But the impurities, you can make it purer and purer. And the density of impurities, as you reduce the density of impurities, this can go up. And so the peak can also go up and all that. So it really depends on the two scattering rates, one over tau due to phonons, and impurity is 1 over tau due to impurities. And the total rate of scattering is, again, approximately sum of all individual scattering rates in a phonon. So this is all occurring in parallel. So you add them, and therefore the mobility is lower than the lowest line here. Okay, so that would be true for a lightly doped semiconductor, and in realistic applications, those are used in PN diodes or things like where you have junctions where you have some doped regions and carriers are moving there. In most field effect transistors, we are not using a lightly doped semiconductor at all. We're using a two-dimensional electron gas typically, or a highly. So in those in most transistors, our Fermi level, for example, we had sketched this sort of a energy band diagram, remember, and the Fermi level was deep inside the conduction band, and we had a certain density of electrons in the conduction band. Those are, if you measure the temperature dependence of those density of electrons, that is really not changing with temperature. That stays almost flat. Once the Fermi level goes into the conduction band, it's called a degenerately doped or degenerately carrier distribution. So the carrier density really is controlled by the gate, not so much by the temperature anymore. So it's created by field effect, not by thermal ionization. So the carrier density doesn't change much. And as a result, the experimentally measured mobilities, let me just use slightly different color, will not. So the phonon scattering will still play a role, but what you'll see is experimentally the mobility will saturate. It will not have a temperature dependence at the lowest temperatures in this material. So only when phonon kicks in, it has temperature dependence, but at low temperatures it doesn't. So I should sketch. So when the carrier, so here's actually a very good rule of thumb that if your carrier density is not changing with temperature, I should expect a mobility versus temperature curve, something like this in general. And that's the carrier density. And the scattering rate, tau, due to phonons, will be proportional to the number of phonons, or 1 plus that. So, and that's basically 1 over the Bose-Einstein distribution of phonons. That's how it's going to be in the end. And if you have a phonon energy that is very small compared to kT, then the denominator is, this e to the power argument thing here is much less than 1. So you can do a little Taylor expansion, and if h bar omega is much less than kT, phonon energy is much less than the temperature you are interested in, then you can see that e to the power x will become 1 plus x, and the whole thing will just be 1 over x now. And what you end up getting is the number of phonons, give or take, is the kT over the phonon energy. So this is just tell you how many phonons you have. At room temperature, if h bar omega is in the acoustic mode, and it's a low energy phonon, maybe 1 MeV here. These are the phonon energies of the crystal, optical and acoustic. Let's say I look at a very low energy, 1 millielectron volt. At room temperature, that's 26, that's 1. So you have 26 phonons. I mean, that's just the average, thermal average of a number that are available for scattering. If the phonon energy is not much less than kT, but it is maybe much larger than kT, and that's possible. Materials like wide bandgap semiconductors, diamond, gallium nitride, their optical phonon energies can be of the order of 90 or 100 MeV, or even 150, 200. That's much larger than 26 millivolt at room temperature, in which case it's the opposite situation. And then your phonon density becomes e to the power minus. I mean, this e to the power are large numbers, so you forget the 1, and you get h bar omega over kBT. Right? So no matter what, you can make a plot of this. This is kind of changing linearly with temperature. I'm saying 1 over tau due to phonons will decrease with temperature, and that's changing exponentially. So it will kind of go a little sharper like that. So you can make the plots of these. These are the phonon scattering rates that I'm sketching here. Okay. And at the lowest temperature, the phonons are much more ineffective. You've frozen them out. Lattice vibrations are frozen out. And so the total. So if I look at a metal, typically metal or a degenerately doped semiconductor, I will look at a mobility curve that will look like that, carrier density that will look like that, and therefore you take the product and get the conductivity, the product of the blue line here and the blue line there. And the conductivity, you can see, or you can think about the resistivity, which is 1 over the conductivity. So if I do that, this is basically a general result, true for pretty much a large class of metals or semiconductors. The differences between them are what are the exact numbers. I mean, where is the peak? What is the maximum value? But the trend is always that's what we are talking about at this point. So for the metals, at low temperatures, you have a certain carrier density, but you have the highest mobility. And because conductivity, let's plot two things here. Let's plot resistivity further. Resistivity is 1 over conductivity, and conductivity is 1 over Q times electron density times the mobility, right? So, electron density is constant and mobility is high. At low temperatures, so this increases at low temperatures, therefore the resistivity decreases. So for a metal, what you will really see is the resistivity decrease continuously, but then it will kind of start saturating, because you see this flattens out here. It'll start saturating and not change much, right? And in some metals, it will, because of things we haven't talked about yet, it will really go to 0, and that's superconductivity now. So it will, and that part we haven't talked about, and we will discuss later. Right? But I mean, this is a trend of most metals that the resistivity. It need not be exactly in the shape I drew, curving upwards. It can be it can take various kinds of shapes, but that's the general trend. At the lowest temperatures, it will start really becoming flatter, because of scattering rate. And this would be called like a residual resistivity at lowest temperatures. And this is a hallmark of what is the impurity density in the material, because it's dominated by impurity scattering, and this part by phonons. Now, but the same thing for a semiconductor, two-dimensional electron gas, for example, will behave in a similar way. In a semiconductor, typically the correlation effects are not as strong. There are some exceptions. So superconductivity may or may not be observed at the lowest temperatures, but it will also have a trend like that. The resistivity will, in a two-dimensional electron gas, it will look like this. So it behaves pretty much like a metal. The mobilities in a metal are typically, if you calculate, the carrier density is high and the mobility is not typically very high. Whereas in a semiconductor, the mobilities can be extremely, extremely high, because the effective mass turns out to be, in some semiconductors, can be very small. The bands can be much more curved at the Fermi level than in many metals, for example. So as a result, the mobilities can get into millions or 10 million for some high mobility 2D electron gases. And you start seeing some more interesting effects like quantum Hall and other things for those levels of purity. In a doped semiconductor, on the other hand, you can see that if I were to multiply, this curve with that curve, things are, it won't quite, saturate like that. It will, become very, very, the resistivity will go up at low temperatures, right? So it will not, resistivity essentially may look something like that, for example. High at low temperatures, minimum, and then high at high temperatures again. Right? Does that make sense? I mean, if you look at this picture, you see that. Electron density is low, mobility is also low, so resistivity is high. Right? And so in condensed matter literature, whenever the resistivity will go up, this would be labeled as an insulator, and that's just the jargon. Whereas the resistivity decreasing with temperature will be labeled as a metal. Right? So metal and insulator. So if in this regime, let's say, so the resistivity, when you lower the temperature, if the resistivity is going down, it's a metal. Resistivity is going up, it's an insulator. And sometimes, if you do careful measurements with 2D electron gases, under certain conditions, for the same 2D electron gas, you can go from one to the other, and that would be labeled as a metal-insulator transition and things like that. This the sign or the temperature dependence is what is used to characterize it as a metal or insulator. Yeah.
This might be a tough question since it's super material dependent, but I'm trying to get an order of magnitude for how much mobility changes with temperature.
With temperature, yeah. So I can give you an example. In fact, let's look at. Say gallium arsenide is a good example because the mobility has been studied a great deal. At room temperature, we'd be talking maybe about 8,000 centimeters square per volt second, right? And if I formed a 2D electron gas with gallium arsenide, at the blue line, this can reach 10 times 7 centimeters square per volt second. So that's 10 million. So it can really change by a very large amount for gallium arsenide. And that requires you to have extremely high purity. This lower limit is also related to defects and impurity scattering. And we are going to discuss some details of it today. But then there are other materials. If you look at gallium nitride, scattering rates can be identical, but the effective mass of gallium nitride is a little bit larger. So then it's 3 times larger, actually. If you look at gallium arsenide, it's 0.07 effective mass. Gallium nitride is about 0.2. So it's 0.07, 0.2. So as a result, and the phonon scattering rate is a little stronger, so the room temperature mobility goes down to about 2,000, for example, which is also actually very acceptable and a good number. And the low temperature mobility is similarly maybe 100, 200,000, not a million, for example, and so on. So it follows the trends here. And silicon MOSFETs, where you have a rougher interface between, for the 2D electron gas, these numbers, the mobility numbers are more like 200 or 300 at room temperature. That's the most common device we use in all microprocessors, so that is about 200. And because the interface is rough, the scattering is not so much dependent on phonons. It is really also determined by interface, so it doesn't quite go up too much. It goes up, but not that much. Yeah, okay. Right, okay, so that's a general trend of things, and we can, for lightly doped semiconductors, this temperature is also what you can call as related to the kinetic energy of electrons, because right, so we'll look into that right now. Okay, so but for highly doped or degenerate semiconductors, is the Fermi energy determines the effective velocity, not the temperature. So that's why for high degenerate, so the changes that you observe with temperature are very large for lightly doped semiconductors, non-degenerate semiconductors, because things can change exponentially. Whereas if you have heavily doped or you're in a metal, these changes are not very large. It's maybe factor of 10, 20, 30. So the residual, this ratio between the, let's say, room temperature and low temperature resistivity towards which it saturates is called the residual resistivity ratio. 100 is a big number, for a metal, for example. Whereas for a semiconductor-based materials we just talked, you can get, 10 to the power 4, 10 to the power 5 or something, sometimes change. So it's very large, yeah. Okay, so let's go back to the Boltzmann transport again and look at, the underlying models we used to calculate and understand and explain the experimental data. Well, I'll just use a few of the slides today to go through and then work out a few examples when it's necessary. So we did talk about the fact that we can write the Boltzmann transport equation in this fashion with all the quantum mechanical scattering rates buried inside these SKK primes and such things. Right? And these are given by the Fermi-Golden rule, right? The scattering rates. And we also discussed that if I have no scattering, if I have no transport, this term, I have no electric fields, no gradients, then these two terms are 0, and I get, the rate of change of the distribution function now that controls, all the controls which states are available for scattering and such. The distribution function is not changing with time anymore. So that's your, thermal equilibrium situation. In which case, that is also 0, and the right-hand side must also be 0, in which case we also identified that the distribution function under those conditions, when you have no gradients, no electric fields, and basically no perturbation, external perturbation to the electron distribution, where the electrons are completely in equilibrium with the lattice itself. Under that situation, the distribution function must be the Fermi-Dirac distribution, right? And that's our, that's the basis of our understanding here. And so, as a result, we are trying to find: is there a relationship between scattering rate from one state, K prime to K, compared to its reverse process, where you go from K to K prime. So, and we found that this must be a constitutive relation relating, that relates the two scattering rates, K to K prime and its inverse process. And so we can take the ratio, and we found that scattering rate for going uphill in energy costs you a little more. So the scattering rate is lower, right? Going uphill. So the ratio between the uphill and the downhill is e to the power the energy difference by kT. So that's what we found. And we have not invoked anything here about what is the nature of scattering. But now if we invoke what is the nature of scattering, physical microscopic process of scattering that leads to this, we can learn something very important right away. And one of the things we can, just go over here. Let's look at this. So we end up with that our picture here is EK. Now how I've sketched that, but this is a exaggerated, picture here. EK prime difference is h bar omega, right? And so we are looking at scattering rate this way and that way, right? K to K prime. Yeah. That's k prime to k. All right. And so what we are seeing is if you're they are related by this e to the power h bar omega by kt. Now, if we say that how is the scattering taking place microscopically, and under thermal equilibrium, the electrons are interacting still with within themselves, which leads to the Fermi-Dirac distribution of electrons, Pauli exclusion principle, all that stuff. But they're also interacting with the lattice, right? They are the lattice of atoms that they're sitting in, and they are able to they can collide and absorb or emit phonons. So they can as they are if we allow, that is the only microscopic process by which it can really change its energy, right? We are not shining any light, not doing any external perturbation. So that's the only microscopic process by which the electron distribution can exchange energy with the heat bath of the lattice, which is the thermal vibrations. And so now, we can ask that what is the rate at which the electrons can absorb energy and promote itself from a lower energy level to a higher energy level, right? And we know that answer is clearly given by the golden rule. We have derived it, the scattering rate, k to k prime. We know that it's 2 pi over h bar, your matrix element, k prime squared. And then we have also said that it's ek prime must be, for absorption, ek plus and h bar omega, one quantum of phonon can be absorbed, right? So this is the scattering rate for one state, k to k prime. Now these are, remember, the k primes are the electron coordinates, electron k's, not the phonon k's. And to find the total, meaning if I say that I have maybe a lot of final states at this energy because the density of states is increasing with energy maybe. So a lot of final states. So you sum, let's say I'm going to just sum over all k prime to find the total scattering rate, 1 over tau, let's say. In which case, the sum over the Dirac delta functions will effectively give you a density of states, right? Or in fact, let's do this. Let's not do k to k prime sum over k prime. Let's do this way. So this is so we go k to k prime by absorbing a phonon of momentum q. H bar omega q. Does that make sense? The q is the wave vector of the phonon. 2 pi by the wavelength of the phonon. K is 2 pi by the wavelength of the electron. So that's the difference. And then we sum it, instead of all final k states, we sum it over all possible phonon states, q's. So in the q states. And when you do that, what you end up getting here is related to, basically what you are getting here is the phonon number, so it's towards the total number of phonons, just like how many electrons are there, electron states are there, you get how many phonon states are there now. And the occupation function and all will take care of the distribution function. We are going to derive that. But what I'm trying to get to is really that the scattering rate for absorption will be proportional to the number of phonons that are available for you to scatter. And that's something, saying something quantitatively that you could have said, qualitatively or heuristically too, that, in order to absorb a phonon, there must be a phonon first. And if I don't have it, there's nothing to absorb, right? So that should be proportional to the number of phonons that are available in the crystal vibrations. So number of phonon modes in some sort of a thermodynamic average at this point. On the other hand, yeah.
So how would you do like an equivalent thing for an electron relaxing and releasing of that?
Yeah, so we are going to now talk, exactly right. So now we want to ask then what is the, so this is absorption, right? And this, now we want to ask the exact opposite process of emission, right? What is the emission rate? We already have from this, analysis we discussed here that any process and its inverse are related by the energy difference. So we can say, even before we talk about phonons, that the emission process rate will be proportional to absorption rate, right? Absorption rate times e to the power energy difference by kT. We can say that right away because we have already seen why. Right? So we know that. And actually, no, this is not proportional to, this is exact. Right? But now we can say that emission rate must be proportional because absorption rate is proportional to the number of phonons. This must be proportional to the number of phonons times e to the power h omega t. That we can say from these arguments now. Right? Now, the other thing is the number of phonons phonons are bosons, so they follow the Bose-Einstein distribution, not the Fermi-Dirac distribution. So the number of phonons is really h bar omega over kBt minus 1. I'm talking about one mode at this point, kind of, not or in that picture at this point, right? So number of phonons looks like that. And you can actually look at, you can just do 1 plus this number, just to, for argument's sake. You do 1 plus this, you'll see, that comes to the numerator, and you get e to the power h omega by kBt over by kBt minus 1. Right? If you just do 1 plus that thing, right? 1 plus the Bose-Einstein distribution. And so that is really 1 plus number phonons is also equal to e to the power h bar omega by kBt times the number of phonons. Do you see that? I mean, if you add 1 to it, you multiply it with adding 1 to it is equivalent to multiplying that number by e to the power h omega by kt for the Bose-Einstein distribution. It's a unique property. Sorry, it is a property. I don't want to say unique, but this is a property of the Bose-Einstein distribution, which models, which is the distribution function for phonons, for photons, for polaritons, plasmons, whatever is a wave. This is, a bosonic wave. This is the distribution function for all of them. So yeah. Now you see now here that that's what's sitting here, right? So you get right away that the emission rate is proportional to 1 plus the number of phonons that are available, right, in the crystal, right? So from here, right, you see that that's what you get here, and we identify this as that term, and so the emission rate, and this is very interesting point because this underlies quite a few interesting things. I mean, this is also the underlying idea behind a laser, and anything that operates in that fashion, because what it's saying is you can dissipate, you can absorb, the electron can gain energy from the bath as long as there is some phonons to absorb. In the same way, an electron can absorb a photon from the electromagnetic field as long as there is a photon to absorb. Right? But to emit, it's 1 plus that, meaning if your number of photons or number of phonons is 0, there's no problem, it can still emit. Right? Okay. It can still emit, right? And so this part, therefore, is called as the spontaneous emission. Right? Spontaneous emission, it doesn't need any photons or phonons to promote that activity of emission. Right? So this is called the spontaneous process. And if you have phonons, it will only help to emit. If you have some phonons, and this is a little counterintuitive, phonons, this is a nature of bosons. If you have 10 phonons around, you can see if you have 10 electrons around, or if you have 1 electron in a state, you can't fill another, right? But if you have 10 phonons in one mode, the probability that you can emit one more phonon into that mode is increased by 1 plus that. So this is a collective effect. So this is so we can say that the number of phonons that are already there will stimulate the emission of more phonons or more bosons into that mode. So this is okay. So that comes out also from this sort of a thermodynamic analysis of Boltzmann transport equation. So the fact that you must have a stimulated and a spontaneous emission processes because okay. So we went through the argument now. So what we invoked here is the bath into which it is emitting, or the energy bath of states into which it is emitting or absorbing these phonons. So this is an absorption of a phonon, that is emission of a phonon. This is a bosonic system. In other words, it follows the Bose-Einstein distribution. That's all we have invoked at this point. Whether it's a phonon or photon, that's a separate matter. We haven't really gone into that detail yet, but it holds for both. So, yeah.
How do polarons affect?
Yeah. So polarons are hybrids of the two. They are neither electron nor phonon, but a mix of two. When the electron, we'll talk about that when we talk about superconductivity, because when the crystal is very ionic, the electron, as it moves, it drags around a cloud of atoms with it. So that composite object is a polaron. So it has a little bit of fermionic, little bit of bosonic nature, both. So we'll talk about that. So when you get into that sort of hybrids, then your distribution function looks different from both Bose-Einstein and Fermi-Dirac. It's not neither. When you have the hybrid behavior, it gets a little properties of both. So, yeah. Okay, so now, and I think this is a very important point, because that tells you why, even though so low field mobility, this value here is because of electrons absorbing phonons that are already there. And so if I make this measurement at a very low temperature, I may get a much higher mobility at low fields. But if I go to high fields, what you'll see is actually this will kind of saturate to about the same value. It won't really, the high field saturation velocity doesn't quite change too much with temperature. I told you for semiconductors you can change by, from 8,000 to 1 million or 10 million here. Not so for saturation velocity. Saturation velocity will be around 10 to the power 7 centimeters per second. And the reason for that is because the low field mobility is dominated by absorption. The electron doesn't have enough energy to emit. It's low electric field. Yeah. But the high field is dominated by this term, emission, phonon emission. When a high field electron has enough energy, it can collide with the lattice and dump its energy to the lattice, set off vibrations. So it will create, it will actually emit phonons. So it's dependent primarily on spontaneous. If there are some phonons, okay, but this dominates. And that clearly has no temperature dependence. It's spontaneous part. No temperature dependence at all. So it kind of clamps there for most semiconductors. And this is an important point. It's, sometimes people, there's a misconception that if you have, so if you can prevent, phonon absorption, if you have a high mobility, you are guaranteed to have a high velocity. That's not quite true. So yeah, the velocity really is much more independent of these things. It's primarily dependent on the coefficients that sit outside, not so much about the details of that anymore. Okay, I wanted to point that out because that's an important argument that comes out just from this analysis, and then the exact details are separate matter. So, is that clear? So temperature will have very little effect. It will have some effect, but not orders of magnitude effect on saturation velocity, but it can have orders of magnitude effect on the mobility. Now going a little deeper into that discussion, if your semiconductor is extremely pure or the metal is extremely pure, very low defects, then this level or that level, which is impurity limited, will go up and up, and so you will get a large change in temperature. Large change in temperature at low field mobilities. But if your material is very impure, a lot of defects, a lot of scattering, then that floor comes down and it starts getting less and less temperature dependent. Right? So that's another thing. So if you're doing this measurement and you see that, oh, I have a semiconductor which is lightly doped, or I have a semiconductor measuring the mobility, but it's not changing whether at room temperature or at 4 Kelvin, it's not changing much. That typically means that you are, if the mobility is not changing much, it means it's highly defective and a lot of defect scattering in the material. Right. So and then when you clean it up and becomes much more pure, then you start. So this is a hallmark of the purity. How much temperature dependence do you have at low field mobilities and all that? So, yeah. Okay, so now getting to the details of the mobility itself. So we look at now, remove this equilibrium condition. We got a very useful information by looking at what happens if all these terms are taken to 0. And now we are going to look at, based on what we learned, a little more detail about this collision integral, because we're going to obviously be more interested in situations when we apply an electric field or there are concentration gradients and things like that. So we want to kind of remove that. So because we now know that this scattering rate and its inverse are related through this e to the power h omega by kt, we can look at this collision term on the right hand side a little more detail, and we'll see that there are two great simplifications that allow for the solution of the Boltzmann transport equation, even though it looks forbidding, but for two conditions you can actually solve it. And we saw that so I've basically taken out this e to the power. I've just looked at k to k prime, and I realized that the inverse process is just that, so I take that out. Right? And now you have f of k prime, and you have this Fermi functions, the products, and e to the power h omega. So now let's look at. I can't simplify it further, except if my initial and final energies are the same, in which case that becomes 1, right? And that is an elastic process, right? Elastic process means the electron is not changing energy. These two are the same. Right? That's a scattering event which could be due to impurities or extremely low energy phonons, extremely low energy acoustic phonons, so very small. In which case these two become the same, and you can see now the products f of k prime times f of k and f of k, that will cancel. The product will cancel out. And you end up getting this relation now, okay, s to k prime. And you can see that there are two terms, and you're summing over all final states k prime. So you can write it in this way. This is our unknown. Remember, we are solving for f of k. We are just integrating or summing over all k primes. So you can write it in this way, that whatever is on the left-hand side of your Boltzmann transport equation, the right-hand side is just that, sum over scattering rates time of f of k prime minus this f of k over tau. And this tau of k, if you look at this relation, is basically just the sum of all scattering rates from k to all final k prime. So what I'm saying is 1 over tau, the way it's defined there, is just the sum of s k to all final states, right? The way it's defined there. And this thing is goes by various names. This is also called the quantum scattering time. Basically, you just whether it scatters by large angle, small angle, you don't care. You just sum over all scattering events, and that's called the quantum scattering time. And this appears naturally in this Boltzmann solution of the Boltzmann transport equation. And the left-hand side, you will have all your field terms and your gradient terms and such to solve for it. The other end of the spectrum is when the phonon energy, meaning this exponential term, is very large. Not 1, but very large. So if h bar omega is much, the difference is much larger than kt. We discussed one of the cases there. In which case now that the product, you can do a little bit of analysis here, and you can show that. If this is a large quantity, and if I look at this product, you have f of k prime, and you have f of k prime times f of k, and these occupation functions are, we remember these are numbers between 0 and 1, always, right? And so if I take 0.8 times 0.5, you can see that 0.5 times 0.5, it's much less than 0.5. So that's the idea here. If the occupation function is much less than 1, you can simplify it even further. This is a large number, so you can throw this one out already, because that's less than 1. And then you can retain only this, but even then you can simplify it even further by saying that if f is less than 1, reasonably less than 1, then this is also true. You get a simplification again here. And what appears here is the sum of the scattering rates, not the quantum scattering time, but multiplied by occupation function of the final states now. And there's a e to the power h omega. The reason these two, so this is a highly inelastic scattering. I shouldn't say just inelastic, because the approximation is, the energy difference is pretty large. So now you can take these and say that I want to solve the Boltzmann transport equation now, and either under this approximation, that approximation. So I go back to the Boltzmann transport equation, and let's look at so if I still am not applying any so let's say I have pulled my distribution function out of equilibrium by applying an electric field, and then at time t is equal to 0, I turn it off abruptly. So what does that mean? I have pulled out the distribution function from its, so here's the equilibrium distribution function. I'm just tracking the distribution or the occupation function of a state k, f of k as a function of time, or k prime, I mean any of the k states. And till this point in time, I had an electric field in the semiconductor or the metal, and that at this time I just turn it off abruptly. And I know that ultimately, given enough time, the distribution function should approach its equilibrium value, and the equilibrium value is the Fermi-Dirac distribution, right? So if I turn it off, right? And then so whatever it was, maybe it was, occupation function was a little larger, and then what I'm trying to say is it should approach the Fermi-Dirac distribution, F0 of energy, with time. Right? And this time constant is what we are kind of trying to calculate now. What is this time constant? So it will look like e to the power minus t by tau. That's the tau we are after at this point. So how much time does it take for the distribution function to go from a non-equilibrium situation to its Fermi-Dirac distribution if I remove the perturbation? And this is the equation that's giving you that at time t is equal to 0, I've turned off my electric field, so all the terms on the left also still kind of go away, and you end up with, this is your differential equation that tells you that. And the time constant is this quantum scattering time that we just wrote down. So that's the time it will take for the distribution function to go from a non-equilibrium to a Fermi-Dirac distribution. And that you can get out of a couple of lines from here. But now if I have a constant electric field, I'm holding the distribution function here. If I have a constant electric field, I've modified it from its Fermi-Dirac distribution. If you have Fermi-Dirac distribution, there is no net current. You know that it's symmetric, right? So when you apply electric field, you shift the distribution function from its, say it was, Fermi-Dirac would be circular in kx, ky. Because of electric field, you have shifted it, and we are trying to find, how much is the shift and all that. We are trying to find the orange circle, if in other words, and the blue circle is the Fermi-Dirac distribution in the k space. And that equation now is, I turn on the electric field now, and so the distribution function, depending on the electric field, what you'll see when we work through it, what you'll see is that the distribution function f of k prime minus f of k, the deviation, or the difference between two occupation functions at different k points will be given by this relationship, where v's are the velocities of each of these k states, the group velocities in the band structure, and this E is small e is the electron charge, E is the electric field, so that's the force times this time constant tau that appears here. So what I wanted to say is that so if the electric field is forcing the electron, so the electric field is, let's say, this way, and the electrons are going that way. If you scatter by a very small angle, then your current doesn't change much, because those electrons still make it to the other side. Right? But if the scattering is by a very large angle, backscattering, then the current gets lowered by a large amount. Conductivity goes down more, right? So transport along the electric field or in the direction of a force is heavily dependent on the angle of scattering. Right? And that is not accounted for in the quantum scattering rate, because that is agnostic to how much angle you have changed. It's just saying, did I dephase, did I change my k or not? It weights everything equally. Whereas if you look at the Boltzmann transport equation, in the presence of an electric field, what will enter in a new sort of scattering rate from just looking at the solution of the right-hand side in the collision integral is you'll get a scattering rate from k to k prime, and then there'll be a 1 minus cosine theta factor that will appear just from this sort of an analysis here with the electric fields, whether the k is initially the k, and maybe the electric field this way, the k was that way, and then it changes, so the k dot e factor, that angle cosine. So the cosine theta is the angle between the initial k state and the final k state, k and k prime. And you can see that if the angle is 0, then you get a 2, so that means that's good. You get a okay, so if the theta is 0, cosine theta becomes 1. If the theta is pi, which is backscattering, what am I saying? If theta is 0, this becomes 0, 1 minus 1. and that means your scattering rate is 0, no scattering. As you know, and whereas if this is pi, it becomes 2, so you have a large scattering rate. So that's the weighting, and this is the momentum scattering rate. So and here S of k prime is just the golden rule result. But here, to evaluate the momentum scattering rate, you must take into account the angle for all scatterings and then weight it with that and then sum over all k states. Now this is the one that enters electron mobility, not the quantum scattering time but the momentum scattering time, because mobility is a measure of how much conductivity you have or current, what is the transport, how good is the transport along the electric field. The mobility is tied to the electric field. So okay. Now there are some details I want to kind of not try to derive it but just describe it. It's also in the posted notes, so please read up on there. Now we're going back and starting to add more terms. So here's the total scattering term on the right side, and you have the rate of change with time in k direction in the k coordinate momentum space. Actually, no, this is the spatial coordinate r, and this is the momentum space, momentum coordinate r. So we also know that we can actually say something very useful again by looking at the whole equation at equilibrium. We know that the distribution function is Fermi-Dirac, and things are not changing in time on an average. And the net collision term is 0. Whenever you are in equilibrium, the net collision term is 0. In addition, each one of them is 0. Right? At equilibrium, and the Fermi-Dirac distribution is 1 over 1 plus this energy EC. This factor G here is just conduction band edge plus any kinetic energy you have, which is the band structure, minus the Fermi energy. You know this one. This is the Fermi-Dirac distribution. Potential energy plus kinetic energy minus the Fermi energy. Right? Total energy minus Fermi energy by this should be the Boltzmann constant, kBT, and I think that you understand. Yeah. So what it's saying is if I just look at the equilibrium and I look at the Fermi-Dirac distribution, I can actually conclude two very important things. That at equilibrium, this is 0, that is 0, so the sum of this and this must also be 0. Right? And we are saying that we can have an equilibrium even with an electric field. And this electric field, and this is very important because in semiconductors and junctions, you don't have to apply an electric field from outside. You can have an internal field. If you build a junction, there's charge transfer and there's a potential drop across a junction, metal semiconductor, PN junction. So there's an internal electric field. Right? So in those structures, for example, or in the most general condition, even though this is 0, this term may not be 0. Right? The f, which means that, but the sum must be 0. Right? You can see that right away, right? So that means that this term and that term must be related. Right? The gradient in k space of distribution function and the gradient in real space are related to each other. Right? So that you get that from here. And how are they related? You can work through quantitatively. You can show that just take the gradient in real space of the Fermi function, and you will get some factors out here because the g. So you take a derivative with real space, and it only acts on this term here, because that's the only spatially dependent term. Band structure depends on k, not on r. Fermi level depends on space as well. So Fermi level can change. So you take the gradients and you work through this, both the gradient in real space of the Fermi-Dirac distribution and the gradient in k space of the Fermi-Dirac distribution. So both of them will involve the gradient in energy space. We are going through energy because it's easier, df by de. And it has a nice expression like this, and you can use it here, plug it back in. And what pops out in the end is a very nice and very important result, that you get the constitutive relation between how the conduction band can move bend in real space and how the Fermi level bends in real space. And how do things change? This part is important. How does we have talked about gradients, so the gradient can be in the distribution function. The temperature on one side of the junction can be different from the temperature on the other side too. So the temperature can also have a spatial gradient, and we allow for that. And this term is responsible for things like thermoelectrics, where you have a temperature gradient and you're trying to generate energy out of it. This term would give you thermoelectric coefficients, for example. But for only internal electric fields, any field will be the negative of the gradient of the conduction band profile. That's for internal fields. It's not because of externally applied voltages. And when you take that into account, some terms cancel. What you get is actually a very simple result, but it's a very nice result. What it says is the Fermi level gradient in space and plus the gradient of a term that involves temperature, gradient of temperature. These two should add to 0 at all times. It's a constitutive relation for equilibrium. And so you can actually have a temperature gradient, you're allowed to. But if the temperature gradient is not there, if the temperature is the same everywhere, in that case, the Fermi level must be constant everywhere. That's the meaning of equilibrium that you can derive from here. Even if you have an internal electric field, the Fermi level is still constant everywhere at equilibrium. And that's an important relation. Now, if you do have a temperature gradient, then you have this additional term. And that means the Fermi level, if I have higher temperature and lower temperature on the left and lower temperature on the right, then the Fermi level has to balance that to get to 0. And that means if by temperature difference, I'm driving a Fermi level difference, and that's the nature of a battery, because what do you mean by Fermi level difference? If I connect an electrode outside, it will flow a current now. Okay? And so the temperature difference can drive a difference in Fermi level, and that means the two ends of this conductor are at different potentials. And therefore, it can drive a current. So you get the fact that, so you can get thermoelectric effects from here. All right, so now, yeah.
How would we talk about you go back to the one you were just on?
Just one?
Yeah. So if we were operating like the orange circle, is the Fermi level just the radius, or is it like the average distance from center, or are those the same?
I see. So in the non-equilibrium situation, so first of all, let's see. The blue one, it's clear there's one unique Fermi level. But in the non-equilibrium situation, it's not completely clear what is the Fermi level, because you can have various, it's non-equilibrium. So it has a Fermi level that for the right going carriers is slightly different from the left going carriers, for example. Right? In the ballistic situation, we have seen that this has one Fermi level, the other has the other, right, source and drain. Here it is mixed up. There's no one unique Fermi level for this distribution function.
So how would we talk about like the spatial variance?
Yeah. So now we're talking about how do you calculate what is the distribution function in this situation, which is when you allow scattering, and how does it mix up, and you deviate from both the ballistic case and the equilibrium case now, right? So that's so what you're saying. So we have at equilibrium a Fermi-Dirac distribution which is symmetric in K, and then you apply a voltage or a field, and you become this one, right?
Yeah.
And now the Boltzmann transport equation is telling you what is that function. You have to solve it to get your f of k, right? So that's the idea. And essentially what we are now looking at is just to be clear, so you have the df over dt here, and the collision integral that we had on the right side, this one, because of the analysis we showed a little earlier, for example, here or here, I can write it for let's say for elastic scattering. Primarily for elastic scattering, what you see is it becomes the right hand side becomes the f, the distribution function. And so you have this is a linear change in the distribution function. It doesn't. So the change becomes f minus its original value by a certain scattering rate, which is the momentum scattering rate. This is the collision term in the relaxation time approximation, only exactly true for elastic scattering. If you have inelastic scattering, you can't do this. But if you do elastic scattering, the collision terms becomes the deviation, the new function which you want to find out, minus the original Fermi-Dirac over this momentum scattering rate. And you plug all this into the Boltzmann transport equation, and here's your new distribution function. after you
Yeah.
solve it.
So I guess what I'm really
Yeah.
curious about is del R. Like, how do you take del R when it's del R of F when it's not centered?
Yeah, so this is the K space, So
Yeah.
if you remember, we are solving for the Boltzmann transport equation in K and X, or K and R, right? And del R, physically, you can really imagine if I have an N-type semiconductor and a P-type semiconductor next to each other, then you know that the electron density is very, very low in the P-type semiconductor. It's mostly holes. So you have a large gradient in the real space now. So the occupation function is solved locally at all R's. So you solve for K's at all R's, and you at all K's you have solved for. Does it make sense? So at each point you have, in real space you have all K's allowed.
Yeah.
Each point in K space you have all R's allowed now. So that's another coordinate going, and you are actually solving for it here. Right?
Okay.
So and this is a full-blown solution now of the Boltzmann transport equation. Shouldn't be equal. It's approximate. It's an approximation. But what you end up getting is something that at least intuitively makes sense, that you have the original distribution function, which is the Fermi-Dirac distribution, and then you have a deviation from it. This part is the deviation. If you have only electric fields, let's forget the concentration gradients for a second. Here's the deviation. You get the gradient of the, look at this bar, gradient of the band structure. This is the band structure over h bar. That's the group velocity. Group velocity times time, that's a length, for example, right? Length times field, or length times force is the energy, right? Force times length is an energy. And this unit-wise, that's an energy, and you get the derivative, the df by the derivative in energy of the distribution function. Now, this is very important, that is the derivative, because if your distribution function is even in energy, and you take the derivative, let's say, I'm talking about f naught, not f at this point. This is the Fermi-Dirac distribution, right? If it's symmetric, then df by de becomes anti-symmetric, odd, if you might. So it will become like that. Does that make sense? That's and we have also discussed this a few times earlier, that only these distributions will give you a net current. This won't. If it's symmetric, it will always add up to 0, right? So always add up to 0. It will not give you current. So this is the term, the deviation or the perturbation from its original value. Physically, you can see here. This is your new distribution function, and what we are really saying also is it also has shifted. Physically, the distribution function has become something like this. It has drifted to the right by how much in energy it is. Everything that multiplies this whole thing, that's the energy. It's proportional to the tau m. If the scattering time is very long, that means I have very few scattering events. It moves even further. If the scattering time is very short, I have scattering very often. It moves very, very little amount. And the net current, now you can see that you can kind of make a reflection around here, and it's carried by whatever is the excess here on the right side. So, and then this equation is telling you exactly what is the function in K space, in energy space, wherever you want it, right? It's the and then. Okay, so if you have concentration gradient, it appears here from the original Boltzmann, and if you have so remember, the force is basically a K-space gradient. This is the K-space gradient. This is the real space gradient. They both appear. Now the problem, just like we were solving for Fermi golden rule, the problem is our unknown is also sitting on the right side now, right? So here in this problem too, right? You can say it's kind of sitting on the right side here. But if you don't have and here, right? Yeah. But for very weak perturbations, this is again an approximation that, and it's actually an excellent approximation, justified by what I mentioned in the last class, perhaps, that you get very close to the measured values of mobilities and all that using this sort of this theory. So one can say that if my distribution function hasn't drifted away too far from its equilibrium value, then df, the derivative, is something that you can, the derivative on the right-hand side, just like we did for Fermi-Golden rule 2, remember, we said that let's approximate this term by its original value, non-perturbed value. So you substitute F naught here, and you substitute F naught here, and then you are free to solve this whole thing. And then everything on the right-hand side is known. So you have solved the equation completely now. That's the approximation under which we are operating here. So, yeah.
With respect to the momentum scattering, so all you need to know is the orientation of your stimulus with your initial final electron states in K space. There's nothing else you really have to consider there as far as determining the angle dependence of the scattering.
Say it again, Joe. I don't think I understood your question.
And so as far as calculating theta, all you have to know is the orientation of your stimulus with respect to your states, and that's it. There's nothing else you have to consider for calculating the angle of your scattering.
Oh, this angle. You mean the angle? So actually, this angle also does not depend on the stimulus. That's kind of interesting too. It really does not. For example, the electric field is, let's say, in this direction, and K prime. The angle is between the electron initial state and the electron final state. It's not really the angle with the electric field. So if I have a band structure, and I have a K point here and a K point here, K1 or K initial, here's a K final. That K has a group velocity going in that direction, that K has and the angle is the angle between them. It's not the angle between the electric field, It's the angle of scattering between the initial and final momentum. Okay, so that's what it is here. So that and the electric field, that comes from the fact that both of them make certain angles with the electric field direction. So yeah.
And so scattering takes into account which states you're scattering it into, which states you're allowed to scatter into.
So those things are taken outside of this picture in the Fermi functions. The angle here is the momentum scattering rate angle is just the angle between the original group velocity of the initial state and the final state. And then you multiply it with all the occupation functions, f of k's in your Boltzmann transport. But does that make sense? I mean, this is not telling you anything. The angle doesn't tell you anything about whether this is occupied or unoccupied. That's dealt with separately. Okay. So I just want to, in the last minute, finish this discussion. I don't think I got enough time to get to the exact nature of the phonon scattering and all that. So here's the solution to the Boltzmann transport equation. Under conditions of near elastic scattering, very low change in energy, and this is a general solution, but on the right-hand side now I'm saying let's put F is equal to F naught. It's in the low perturbation regime. And once you do that, you are actually now able to calculate all the parameters of interest like current density and mobility and things carrier density and all that, because you know everything on the right side. You know the distribution function now. Right? So if you know the distribution function, you just take the group velocity of each k state, multiply, and sum over all states, and you got your current. And I've asked you to look at what happens in different dimensions. If you go to 3D, 2D, 1D, you can show that in general, in d dimensions, you get an expression like this. Current is related to the carrier density. You can pull out the carrier density, and whatever sits here is now your mobility, whatever sits here. And you have the momentum scattering time due to phonons, due to impurities, all that stuff from Golden rule. So now, just going through the whole picture again, Boltzmann transport equation gave you this quantity, Fermi-Dirac plus an excess, and the momentum scattering rate here that goes into this is, we discussed this today. Quantum scattering rate is something you can actually measure in magnetotransport and such things. We will talk about it when we talk about quantum Hall effect. At this point, this is the momentum scattering rate. And physically, quantum scattering rate is also the relaxation time. If you remove your perturbation, the time it takes for the distribution to go back to its original value. In pictures, because of an electric field, your distribution function was here. If I turn off the electric field, it has to go back to this blue Fermi-Dirac. And quantum scattering time tells you how much how long is it going to take to go back there. So, and then the scattering rates themselves are microscopically given by the golden rule, and that's basically you plug those in here to calculate your tau m. The golden rule will give you that. Then you plug in here, get f of k, sum, and get your current. That's the procedure for this. Current or mobility or any of those parameters. So mobility, as I mentioned, you pull out the carrier density and whatever is left here, you have a field, carrier density, electron charge. Whatever is left here is what we define as the mobility. So that's all. Okay, so I think I'm out of time today, but I wanted to discuss all the scattering rates as well, a few of examples, and I know I've asked you in the assignment. So what I'll do is I will have to extend the due date because it's due on Monday, probably. That's what I said. So I'll make it Thursday, and we'll spend one more class. Is it a week from Monday?
Yeah.
Oh, then we're good. Then we're good. No worries. Then yeah. Somehow I'm not time ordered right now. Yeah. So okay, good. No problem. So we will discuss some of the scattering events before we go on to the other topics I discussed, where superconductivity and all that. We'll talk a little bit about the details. Thank you.